My name's Jack Fitzgerald, and I'm a senior scientist with Amazon Alexa. Today I'm going to talk about simultaneous slot filling, translation, intent classification, and language ID. So let's talk about a one use case of natural language understanding, namely a virtual assistant type system. So with a virtual assistant, you would have some sort of audio coming in from the user, raw audio. That audio would go through automatic speech recognition, which would convert it into text. So perhaps the utterance is call Bob. That text would then feed to natural language understanding, whose job is to determine the intent and the slots and perhaps a few other things from that text. So in this case, the intent would be to make a call, and the slot would be, it would determine that Bob is a contact of some type. So from there, you would probably have some sort of arbitration logic that would choose the right downstream skill to handle that sort of intent in this scenario. So perhaps you would have a calling skill, and that calling skill would then probably look up Bob within the user's contacts and maybe determine that Bob Jones is probably who they're trying to reach. From there, the um, system would make the call to Bob Jones from that particular user. Now, traditionally with NLU, the input language is maintained as the same output language. So if we look at this example over here, a bit of a different example from our ATIS data set, we see that for a Chinese input utterance, the intent is going to be language agnostic, but for the slots, we're really just labeling the text. So the same text gets output, but just with some labels. So when that's the case, you can imagine that as you're starting to scale up your languages, um, all of these downstream components, whether they're system components or individual skills, will need to be able to handle all of the different languages that the system can handle. And so as you start to scale up to lots and lots of languages, you could see this as becoming burdensome to these downstream skills. Similarly, as you start to increase the number of skills, that kind of aggregate burden increases. So the idea with this project is, what if we could use a single NLU model that could both classify the intent and extract the slots while also translating the content of those slots. Now, you could also do this perhaps with a separate translation model that was, before or after NLU, but that would add latency, and there's also potential alignment problems. So what I really wanted to see is just, use one single model to do all of this. For the dataset, I used a public dataset called Multi-ATIS++, so that's from Zhu this year. It is based on previous iterations of ATIS, which is kind of a classic NLU dataset. I considered 7 languages from the dataset, which has 17 intents, about 4,500 training examples per language, and I converted all the data into a fully text-to-text format, as shown here. So it's somewhat similar to the approach of T5 or some other papers. So basically you have your tokens, and then those are followed by the labels as part of the sequence, and all of that's followed by kind of special tokens for the intent and for the language. For modeling, I use the multilingual BART model, so that's a fairly new model from Facebook. Because of the translation portion of the task, I wanted a full encoder-decoder model, which is what MBART is. MBART was trained on 25 languages using a 1.4 terabyte corpus of scraped website data from Common Crawl. They used mask language modeling and sentence ordering to pre-train the model. And they also use sentence piece tokenization. Sentence piece is an open source package, and it's great. In terms of my fine tuning, so I did use 8 V100 GPUs, and you can see some of the hyperparameters here. I probably don't have time to go over these, but you can certainly read them quickly here, and they're also available in the paper. So now let's talk about results. So the first thing I wanted to see was how does this system compare with the state-of-the-art monolingual systems? So you can see that here. So these systems right here are kind of the state-of-the-art English-only systems. And the performance on English is not terribly worse than those. So for intent classification, we see 96.98 versus 97.9 there. And then for slot filling, 96.1 for state of the art versus 95.03. So that's interesting to see that we're not, too far away from the monolingual systems, but really a more fair comparison would be to compare to Zhu's system, which also supports multiple languages. So if we look again at non-translation, so when no translation is performed on the slot content, we see that versus the state of the art, so Zhu's system, we're slightly better for intent accuracy, so 96.07 versus 95.5, but slightly worse for slot F1, so 89.87 versus 90.81. But you can kind of see we're in the right ballpark in terms of performance for non-translated slots, so the traditional NLU case. What we really wanted to know for this study is what's the effect of adding the translation component. So for that, you can see that here. So when we add translation, intent classification accuracy degrades by about 1.7% relative here. And then for slotting F1, we degrade by about 1.2% relative. So there is a degradation, but it's not so bad that it's something that means this task is kind of out of consideration. It's a little bit of a degradation, but still very promising results there. Now for language ID, model did great. So 90, over 99.5% average accuracy. In some cases, not surprising. So Hindi and Chinese have their own unique scripts, so not surprising it got perfect performance there. But then also did well for the Latin script languages. So in conclusion, this work demonstrates that a single NLU model can perform simultaneous slot filling and translation while also doing intent classification and language ID using a fully text-to-text data format and a encoder-decoder model proven on the multi-ATIS++ dataset. By adding translation in addition to intent classification and slot filling, intent classification degrades by 1.7% relative and slot F1 by 1.2% relative. Now these results are definitely promising. However, the multi-ATIS++ dataset only contains about 455 unique entity slot pairs. So, it's possible that a model that's this expressive, such as MBART, is really just able to memorize some of those outputs and perform well in that regard. So, to really test out this new task of still, it would be great to have a data set that includes free form and varied content, such as text messages and song titles, open domain questions, things that would really stress the translation component of the task. And so I think that will be a great next step for future work. Additionally, I think for a future model, you'd want to output both the translated and untranslated slots. You can imagine, for example, a text message, you would want to not translate in that case versus you would translate in other cases. So we're about out of time, but definitely happy to connect with folks here at the conference, and it's a pleasure and honor to be here. Thank you.